Fundamentally, there are two areas of vulnerabilities that quantum computers expose in modern cryptographic stacks. First is key exchange algorithm. So when two parties begin to communicate and they want to establish a secure channel, they typically use asymmetric key exchange such as RSA or Diffie-Hellman with ephemeral keys to build common secret that then would be used for the rest of the communication. And those mechanisms typically rely on factorization of prime numbers or discrete logarithms with elliptic curve cryptography that are known to be vulnerable with for large enough quantum computers. Now, today, these quantum computers do not exist. However, the key issue here is that attackers could capture secure communications today, store those packets until sufficiently large enough quantum computers will be available, and then use them to crack open this historic communication and discover information that was carried over. And if these quantum computers will be available soon enough, then this confidential data could still be sensitive. And disclosure of that confidential information could, of course, create harm for organizations or users that perform these transactions or communications. There are other aspects that are important to note that are also vulnerable to attacks from quantum computers, primarily related to digital signatures that are used in certificates that are used in communications to authenticate parties, in identity tokens, SAML assertions, and many other areas of modern security stacks. However, digital signatures do not carry these harvest now, decrypt later kinds of attacks. They will only become an issue only once quantum computers are available. Now, going back to the most pressing threat, the threat of quantum computers posing an issue for data that we transfer today. So there are algorithms that are now standardized that are known to be as secure against quantum computers as they are secure from attacks performed by traditional regular computers. Most of these algorithms are based on a mathematical problem of module lattices. So NIST standardized one of those algorithms that was originally called Kyber's crystals. Now it's called MLCAM, Module Lattices Key Encapsulation Mechanism, or FIPS 203. And now most regulators of all the countries agree that this mechanism is acceptable, is secure, and should be adopted. IETF recently started work on incorporating, embedding this mechanism into protocols. Now here at Zscaler, we of course working at upgrading all aspects of our platform to support so-called hybrid key exchange, when we will be able to combine traditional key exchange mechanism with MLCAM, so that our customers would get the best of both worlds. The attackers would need to crack both elements, the traditional elliptic curve cryptography as well as MLCAM, to get into secure communications that is carried over. And it's not just to help customers who are running modern operating systems, modern software. It will also help customers who run some legacy systems that cannot be upgraded but needs to be secured. We can encapsulate traffic of those systems into post-quantum safe, quantum-safe tunnels that leverage post-quantum cryptography, take it into zero trust exchange, and then from zero trust exchange establish an outbound communication with quantum-safe algorithms. Another very important area that is often overlooked is visibility. Now, of course, we can dive straight into securing things, but many organizations run very sophisticated, non-homogeneous infrastructure. They have lots of different pieces of software, services, appliances, users working from everywhere on different devices, and everything is expected to be, of course, secure, and that involves using modern encryption protocols. So we also provide our customers with visibility, so they would be able to identify those pieces of software, those users that needs to be upgraded modernized, that might need to have certain pieces of software replaced in order to support post-quantum cryptography, so that organizations would be able to take phased approach and understand this problem space better. The first phase is, of course, my recommendation is to take a phased approach. The first phase is gain visibility, understand what needs to be upgraded or replaced. There are certain prerequisites that you cannot just enable post-quantum safe cipher and then magic happens. In many cases, you need to upgrade underlying software, underlying technology. In some cases, you might need have even to replace certain pieces of hardware. For example, TLS protocol, that is de facto standard for secure communications over the internet, can support post-quantum cryptography only in its latest version 1.3. So prerequisite is first to upgrade software to run TLS 1.3 before post-quantum cryptography can be enabled. So to do the assessment, to get visibility of internal and also external resources, cloud services that are being accessed, critical websites, SaaS services, IaaS services, that needs also to be modernized or replaced to be able to leverage post-quantum cryptography. Second step is, of course, enabling PQC. And again, my recommendation is to do that in a phased approach, to not just enable it absolutely everywhere. If something goes wrong, then of course consequences can be quite dramatic. So establish a pilot group or pilot group of users or devices, enable post-quantum cryptography there, observe that everything is working smoothly and correctly. After enabling post-quantum cryptography, there are certain changes to protocols that happen. One of the challenges of post-quantum cryptography that keys are much larger size. So in traditional RSA or elliptic curve cryptography, key shares are few hundred bytes. In post-quantum cryptography, key shares are often kilobytes, if not dozens of kilobytes. Now, of course, with gigabits that we have available, this feels like a rounding error. However, what that means is that this communication needs to be sliced into packets. The biggest packet size is 1500 bytes. So, and that might create a problem for certain inspection appliances, especially if they're legacy. That's why the recommendation is doing a more gradual, phased adoption. And then my last recommendation is get a sense of urgency, get a sense of priority on it. Maybe create a task force within your organization to assess this problem, to build a strategy, and to begin migration. Not just wait and see until regulators will start mandating that. There is high degree of uncertainty associated with when sufficiently large enough quantum computers will arrive. It might happen in a year, unlikely, but could happen. It could happen in 5 years, it could happen in 10, in 100. It's impossible to predict. There is a lot of serendipity involved in research. There are lots of engineering challenges that needs to be overcome to build sufficiently large enough quantum computers, but the consequences for security for cryptography will be quite dramatic when that leap happens. So organizations need to be prepared as soon as possible.